Welcome to the Excel practice video for dependent samples t-test. I am already in Excel and you can see that I have SAT scores for time 1, SAT scores for time 2. I'll post this file so you can walk through this as you want. As we discussed in the video, one of the key parts of doing the dependent samples t-test is creating difference scores. And so we want to know for this individual, what is the difference in their SAT score from time 1 to time 2? So at time 1, they made a 555. At time 2, they made a 563. And so we see a difference of -8. So scores at time 2 are higher, and thus we end up with a negative number. Once we create that first one, we can grab the bottom, drag this down, and it will copy that formula where we subtract time 2 from time 1 for each person, and we can double check that's working properly. At C30, we are subtracting A30 minus B30, so it seems like it's working properly. You could check more, but we've used this enough that you probably are feeling comfortable and confident with that. I put in the alpha level. I also put in t-critical. In the video, I used a more general table that had degrees of freedom for 20 and degrees of freedom for 30. And when we did that, we ended up with our t-critical being negative 1.73. Here, I've gone back to SPATS, looked in Appendix C, looked at Table D, and it gives me the exact t-critical for 29 degrees of freedom, which would be preferable. Where are those degrees of freedom coming from? Again, it's based on the number of difference scores. So if I count from C2 to C31, then I can see how many different scores are there. Is anybody missing? We have those different scores. You can see over here that I have more included, and so you could adjust that to 31 now that we know where that's now that you know where that's ending. And we could adjust this for each of those. The reason that's there is I originally pulled some of this from the one sample t-test, and I've left the one sample t-test here so that you can make some comparisons about the formulas and realize that really one sample t-test, we are looking at, does this average differ from our population mean? But the general process, the math behind it, is very similar to, does this difference differ from 0? And so this helps you to more clearly see, so you can compare and contrast what we're doing with one sample t and what we're doing with dependent samples t. And once we create these different scores, much of the process is the same. So I have the number of different scores. Degrees of freedom is the number of different scores minus 1. And when we look in that chart, the more specific amount for the t-critical is negative 1.699. Part of the reason to get the more specific number is we're going to make the lower limits and the upper limits match what you'll get when you look at the SPSS video, so you can compare and contrast your findings in Excel and the findings in the SPSS video. If we're looking at the mean difference is simply going to be the average from C2 to C31. We see that the mean difference is negative 2.5. So it seems that on average, individuals' scores from time 1 to time 2 are improving by 2.5 points. The standard deviation of the different scores from C2 to C31 is 2.8618. So most of the scores, about 68%, and you can go where we talked about the Z distribution, about 68% of the scores are going to fall between, so negative 2.5 minus 2.86 will give us about a little below 5.36, and then a little above 0. So most of the scores are going to be happening in there. That's the change that we're seeing from time 1 to time 2. The effect then is going to be this difference minus the difference in the population. Again, if it's not specified, typically we are looking to see, is this different from 0? So if there was no change, which if we didn't do anything, if we didn't improve individuals' performance from time 1 to time 2, what we would expect to happen would be that there would be no change. Well, no change would mean that whatever the original scores were, the difference from time 1 to time 2 would be 0. So you can put that in there as a reminder of what we're doing. You can leave it out. You'll get the same number either way. And then the error term. So the error term is going to be the standard deviation divided by the square root of the number of different scores. And so we see that that is 0.5225. We then get t obtained by taking the effect, dividing by that error term. So now we see that our t obtained is negative 4.7848. Importantly, this t obtained value is more extreme, rarer, and in the correct direction compared to the t critical value. So if we drew that normal distribution, we put our cutoff at negative 1.699, the tail end of the distribution beyond that, negative 4.78 would fall in that area beyond it. And so because of that, we know that this t obtained is significant at an alpha of 0.05. For Cohen's d, we're simply going to take the effect and then we're going to divide by the standard deviation of the difference. And so from this, we can see that most individual scores are changing, and in fact, they're changing by 0.87 standard deviations. So from time 1 to time 2, we're seeing a change of about 1 standard deviation. And then when we look at the lower and upper limits, before I've mentioned the idea of absolute values. And in some cases, that is important for calculating the lower and upper limit, because if t critical is negative, which it is in this case, if I multiply a negative value times whatever my standard error of the mean is, then what ends up happening is I end up with a negative value. I then subtract a negative value. Well, if I subtract a negative value, it's actually basically like adding. So if I consistently want my lower limit to be when I subtract t critical times the standard error of the mean, I need to make it the absolute value of t critical to account for the fact that t critical can sometimes be negative. So I'm going to copy this since I'm already clicked into there. And so from this, I see the lower limit is negative 3.3877, or rounding negative 3.39. What that tells me is that if I sampled again, so if I went back and got another group of individuals, I had them take a statistics course, I looked at the change in their SAT performance, they wouldn't change exactly by negative 2.5 points, but they would change somewhere between negative 3.39 and then the upper limit. And the upper limit is the same general formula except we add. So they're going to change somewhere between negative 3.39 and negative 1.61. What that tells me, importantly, is that their change is going to be more than 0. This range between the lower limit and the upper limit does not include 0. It is less than 0. The expectation from the alternative hypothesis presented in the lecture video was that the difference should be less than 0. Thus, this is consistent, and we would say that we reject the null. We reject the idea that they are not improving. They are, in fact, improving, and their scores from time 1 to time 2 are improving probably somewhere between negative 1.61 points and negative 3.5 39 points.